Okay, so in the last class, we were discussing about the maneuvering models. We particularly talked about the added mass, and we looked at our so-called equations of motion when the added mass is included. So we have the added mass matrix added, and we have a corresponding Coriolis and centripetal matrix due to the added mass also coming into the picture. We'll also introduce a damping into the system. And if in case we are considering any of the sea-keeping modes, then we'll also have to include a hydrostatic stiffness vector. And then we could separate out the external forces acting on the system as one due to the wind. So those are the generalized wind forces. You have the generalized wave-induced forces, and then you also have the control inputs. So these are the things which you will use to control the vehicle to track a desired path, or if you want to maintain a certain orientation and position, you'll be applying control forces through these control inputs. Okay, so we looked at what the added mass matrix looks like and how we can parameterize it in terms of we can parameterize the Coriolis matrix due to the added mass in terms of the mass matrix or the added mass matrix. And we looked at how these terms came about and how these expressions for these terms has come about. We are basically using the idea that this parameterization can be used where we are subdividing our 6x6 matrix into 4 3x3 submatrices, and it can be observed that these are all skew symmetric matrices. And that gives us the idea that we can express them in terms of skew symmetric matrices, and we call this vector A1 skew symmetric matrix formed due to matrix vector A1, A2 and A3, and this 3x3 matrix here can be assumed to be a skew symmetric matrix formed by a vector B1, B2 and B3. And we saw what is the expression for these A1, A2, A3 and B1, B2, B3 in terms of our added mass matrix terms. So you can see that here we have all the added mass matrix terms appearing like xu dot, xv dot, so on and so forth, which are nothing but, we discussed about these, that they are derivatives. So this actually represents the derivative of the sway force with respect to u dot, and so on and so forth. So that is the convention which we are using to define these different added mass terms. So we looked at the idea that the total equations of motion can be written in this format, where we now have included the effect of ocean currents and we have combined the two mass matrices. So this M matrix now is a sum of the MRB matrix and the MA matrix. So we are taking the rigid body mass matrix and the added mass matrix and adding them up to call it the M matrix. Similarly, we can do the combination also for the Coriolis matrix. So we have the Coriolis matrix due to the rigid body, and then you have the Coriolis matrix due to the added mass. They both add up to give you the Coriolis matrix of the combined system, and that gets multiplied by the velocity vector plus the damping times the velocity vector plus the hydrostatic part is equal to the control inputs plus the wind forces and the wave forces. So we have just simply simplified the notation here. So instead of mass matrix having two components, we are writing it as one single matrix. Similarly, the Coriolis matrix also is written as a single matrix. Notice that this can be achieved primarily because of that idea that this centripetal matrix can be represented to be independent of translational velocity. When that is possible, we can represent this in terms of VR, where VR is the relative velocity. Relative velocity vector with respect to the currents. So we are kind of taking currents into account, ocean currents into account. The main assumption behind this is that the ocean currents are irrotational. Only in this situation we can get away with this. If the ocean currents are rotational, then you can't get away with this. But for most practical purposes, this assumption is more or less valid. So that's why it's useful to have this in place. Okay. I guess this is where we were, and then we started to look at the idea that when we have a surface vessel where we are only really interested in the horizontal modes of motion and we are primarily interested in surge, sway, and yaw, we can neglect heave, roll, and pitch. So our system reduces to a 3 cross 1 vector, and the generalized velocity vector now is given by UR, VR, and R. So this was a mistake which I had pointed out last time too. And then you have your added mass matrix as XU dot 0, 0, 0, 0, YV dot, YR dot, NV dot, NR dot. You notice that the surge mode is decoupled from the other modes, and we discussed about this idea that due to the port starboard symmetry, you don't expect to see anything happening in the surge should affect the yaw and the sway. And then the corresponding added mass matrix in case of a 3 degree of freedom model is also derived. You can kind of see that if we go back and substitute these values into the CA matrix and take the assumption that we are getting rid of the heave, roll, and pitch terms, and then the surge is decoupled to the yaw and the sway, you can kind of get back what you see as here. You can get back this matrix out of it. We also tried to derive the generalized force due to this Coriolis vector, so where we multiply this matrix with the velocity vector, and we looked at what is coming out, and we identified that there is a term here which comes out as mxu dot minus yv dot times ur times vr, and this moment, this portion of the term which is contributing to a yaw moment due to the hydrodynamic added masses in the surge and the sway is known as what is called as a monk moment. And this pump moment usually has a destabilizing nature, and we discussed the idea that this is not what we are going to delve into deeply. We are only having a brief discussion about this. The true hydrodynamic reasons for this occurrence are not within the scope of this course. It only is important to understand that such a moment exists and it has a destabilizing nature when we are looking at the dynamics of the vessel. Okay, and I think that is where we left off in the last class. Are there any questions so far? Any questions so far? No questions? No? Okay. All right. Is everybody comfortable with this idea of what we have looked at so far as the equations of motion? Everybody is comfortable with this form? It can seem a little daunting when we look at it, but I hope that everybody is more or less comfortable with this form. Yes? No?
Yes, sir.
Okay, good. So we have primarily talked about the mass and the added mass and the Coriolis terms. Today we'll ensure into a slight discussion into the dissipative forces. So we'll spend our time today basically talking about this term. But before we do that, we looked at the 3 degree of freedom model for the surface vessel. Just also let's take a look at what happens to the underwater vehicles. So in case of an underwater vehicle, you typically will assume that the added mass matrix is a diagonal matrix. That's a good assumption to get away with, particularly because we are deep in the ocean and you don't see this different modes coupled with each other due to the symmetry of most underwater vehicles. So it is a good, decent approximation to get away with, where we can say that the added mass matrix is a diagonal matrix. In that case, you will also see that the Coriolis and the centripetal matrix also simplifies a little bit. Although the only thing which you have to consider here is all the 6 degrees of freedom do need to be considered when you're dealing with an underwater vehicle, because you can actually have pitch and heave motions depending on if you are going down or going up or operating at a depth. So you might want to be including a 6 degree of freedom system in order to account for the dynamics. One of the main reasons why we want to not worry too much about the off-diagonal terms, it is time consuming to evaluate them. Although if you have a potential theory program, you can evaluate them and you can actually incorporate them. But you'll find generally that the cross terms have much smaller magnitude. So it's not that much worthy of our time, or it doesn't affect the dynamics significantly. So the dynamics is not too much changed, even if we chose to neglect the off-diagonal terms in the added mass matrix. Okay, so this was only a brief discussion about underwater vehicles. For our purposes, we are mostly be looking at the surface vessels for now. Okay, all right. So coming back to the idea of the dissipative forces, we'll try to take a look at what are the different dissipative forces which come into the picture when we are dealing with a surface vessel and how to model these effectively. So if I go back to our equations of motion, you see that this dissipative vector here is taken in general to be a nonlinear vector, right? Because you have the damping matrix which actually depends on V, and then you're multiplying that with V, which means that this term is not a linear term. It may have linear components and also may have nonlinear components. So we'll try to understand which components can be taken as linear, which components have to be necessarily taken as nonlinear, and what effect will they have on our dynamics. We'll try to think about those as we go forward. Okay. One of the first dissipative forces that we typically have to account for when we are dealing with surface vessels is so-called potential damping. So this is basically radiation damping due to the energy carried away by the waves generated due to the body motion. And you have seen this very well before. We have had a discussion in this course, and also possibly you have seen them from other courses like ship motions course or your statics and dynamics course, where this potential damping is a frequency dependent damping, which means that depending on the frequency with which we are oscillating, the damping experienced is actually different. Now, this potential damping is considering that the fluid is actually inviscid in nature, which means there's no viscous forces which are coming into play here, and we are primarily only interested in the damping due to the radiated waves taking the energy away from the system. Is everybody with me on this potential damping?
Yes, sir.
Okay. All right. What about the others? I only heard one yes.
Yes, sir.
Yes, sir.
Yes? Okay. All right. Could I see you guys for a minute? All right. Okay. This is much better. You can see your faces sometimes. Like to see it at least once in a while sometimes. Okay. The next thing which we discuss is the skin friction damping. Now this is the part which is coming due to the viscous effects. So this is caused due to the so-called laminar boundary layer formed during a low frequency motion. Now this damping is also frequency dependent in general, although we don't understand precisely how the frequency dependence comes into the picture. We don't always fully appreciate what is going on with it, right? We have to approximate it in terms of some uh, Reynolds stress function and to find out some drag coefficient and then be able to apply it. But the precise dynamics of it is not always very clear, especially with respect to the frequency. Okay, we typically usually deal with a uniform flow past the vessel and make an approximation based off of that. But a full-blown approximation of how an oscillatory flow behaves across a vessel can be studied really using CFD and other tools, but we generally don't embark into that direction for the purposes of our modeling systems. Okay, again, this is a linear frequency dependent damping terms. So notice that both these terms which we have so far discussed, they are both linear dampings. So this is linear and this is also a linear damping. All right, okay. Now, when I talked about the so-called skin friction in the laminar boundary layer, you might be wondering, so what happens when the system becomes turbulent? What happens when we actually start to see that the motions are much larger and we are seeing a turbulent motion occur? In that case, is the linear damping still valid? Not really, right? The moment we are looking at large motions where the Reynolds number is much higher, we know that the flow will be turbulent in nature. And when the flow is turbulent in nature, the linear dependence also fades down. You will find that typically that you will have a quadratic or a so-called nonlinear damping, which is coming due to the skin friction. So you may have a linear damping, a portion of it is linear because of the when you're looking at the so-called laminar boundary layer very close to the boundary, but as you move further away, you see the turbulent boundary layer pick up, and where you start to see the effect becoming more and more quadratic in nature. The drag is more quadratic in nature. So when we want to model this, both these phenomenons, our damping matrix will have some linear component and will also have some non-linear component due to these phenomena. I hope I'm making sense here. Yes? All right. Okay. The other type of damping which one must need to account for is called as the wave drift damping, or this is originating from the so-called second order mean and slowly varying forces. Okay, so you can think of this this thing as typically in search direction it has major importance. In the other modes, it is not as important. So the idea here is that let's say I take my hull and it's moving at some forward speed in calm water, versus I am moving the same hull with certain forward speed into waves. Okay, so in one case, my hull is moving forward, but the water is calm. There is no waves on the vessel. In the other case, I have actually waves which are coming at me and I am moving forward with the same speed. Will the resistance in both cases be the same? It will not be, right? There will be some difference. Which one will be higher? Which one do you expect it to be higher?
The second one will be higher.
Probably,
The second one where the waves are coming at it, right?
Yes.
So there is a difference in the total resistance that I measure with the waves and without the waves. Correct? That change in resistance or that difference value is what we term as added resistance. Okay, and that added resistance is a force which is acting on the hull towards this side, right? It's trying to slow your ship down. Now one might wonder, sir, we discussed about waves and wave theory so far. We have read is that it is moving in orbital motion, so the ship is actually doing some sort of a thing like this. Why is there a force in this direction? How is the force in this direction coming into the picture from a linear wave theory point of view? That might be a question which might be coming in your mind. And the answer to that is this is not a linear part. We are here talking about a second order wave forcing. Okay, so this is not due to the linear part of the linear wave theory will not generate any force on the ship in the backward direction. Actually, it should generate zero force because it is periodic in nature, right? But the moment you incorporate that so-called second order wave, where the wave is no longer a pure sinusoid, right? If you actually look at the real ocean waves, if you ever go to the beach and see, you'll find that the peaks are a little more pointy and the troughs are a little more shallow. It doesn't really look like a sinusoidal wave. Yes? Everybody has observed this at the beach?
Yes,
How
sir.
many people have actually gone to the beach? Yes, everybody has gone to the beach, right? Yeah. So you have observed that generally the waves are a little peaky in nature and the trough is a little more shallowed out, right? So that wave is no longer linear. You actually need to account for a higher order wave theory or at least a second order wave theory or even higher orders in order to account for that peaky nature of the wave. Now, the moment you're dealing with those peaky nature of the waves, the forcing acting on your vessel is no longer sinusoidal in nature. Okay? There'll be a mean component which will be acting on the hull, which is trying to slow you down as the waves are coming this way. So, which means that if I just left the vessel as is and the waves were coming as on, you'll see the vessel slowly drift backward. Is that making sense? So we are interested in that little force which is actually pushing you back. Yes.
So is it because of the waves or the current that the ship goes back?
It is because of the waves. This we are only purely talking about the waves. I mean, we are not talking about the current as of now. Even when there is no current, but you have the waves coming at one way, you'll see that the vessel slowly drifts away. You think of it if you went to the beach and threw a frisbee in it. What will happen to the frisbee? Will it just bob up and down there? Usually not. You see that it will drift away, depending on which direction the waves are and which direction the wind is blowing, right? So in a similar manner, when you have vessels at sea, these waves which are a little more peaky in nature, which are not linear, so-called conform to the linear wave theory, you'll see there is some mean force acting on the vessel, and these are called mean drift forces. Okay, and these drift forces need to be accounted for if we want to really model the full damping in the matrix, because these forces will tend to move your vessel in different directions. So that second order component is what we are considering here. So that is why they are called second order mean and slowly varying drift forces. You can think of this in the sense that if I have two waves which are coming together, okay, so if I have, let's say, A1 cos omega 1t plus A2 cos omega 2t, right? Now, if I were to combine them together, or let's say that I had a slightly different phase between, or let me just call this sine. Okay, and let's say that they were both of the same frequency. Can I write this as some amplitude times sine of omega 1t plus some phase angle phi. Can I write it like this? Yes, no?
Yeah. Yes.
Yes. What will be A1 in terms of A and phi?
Mm,
What will be A1 in terms of A and phi? Try it out.
A will be root of.
Sir,
One at a time. Anand,
sir, I got A1 equals A2 cos phi.
A1 equal to A2.
Cos phi.
No, but I wanted A1 in terms of A and phi.
Okay.
Joel,
Oh, sorry, sir. A equal to A2 cos phi.
sorry, come again.
A equals A2 cos phi.
A equals A2
A2
cos
cos
phi. A equals A2 cos phi. No, that's not quite right. I wouldn't think so.
Cos 5 A2.
A cos 5 is A2. Correct. Right? A cos phi will be A2. If I expand this fellow out, I should get A times sine of omega 1t times cosine of phi plus A times sine of phi times cosine of omega 1t. So A sine phi will be A1 and A cos phi will be A2. Right? That is how I'll get it. Right? Now suppose I modify this relationship where omega and so the two signals that I'm adding, they're no longer the same. So instead what I do, yeah, so let's say that I add A1 cos omega 1t plus A2 cos or sine, let's say omega 2t. When I add these two together, what do I get? I want to express the whole thing as some product of cosine of something times t plus sine of something times t or something of that sort as a single product. So where I'm not having these addition of two signals, I want to combine them into a single system. So what will that expression look like? So for convenience, let's do one thing. Let's take A1 and A2 to be equal in this case so that the math simplifies a little bit. And let's try to see what comes. Try it out.
Sir, what should we do?
I want this to be expressed as a single product of sine or cosines with no plus terms. So you now right now see one term plus another term, right?
Yes, sir.
I want to express that as a single product of trigonometric functions rather than a summation of the trigonometric functions. So what will I get? So the idea being that can I simplify this particular expression? Okay, are you able to see my screen? What we have done here? What have we done? We started with these two, omega 1 and omega 2. I expressed omega 1 as omega A minus omega B, where omega A is the mean of these and omega B refers to the difference of these. Correct? Right? Now, omega 2 similarly can be expressed as omega A plus omega B using the same notation. Is everybody with me so far? Yes? Okay. Now what we are doing, we are taking back our original expression. A cos omega 1 t can be now written as omega A minus omega B into times t. Plus A sine omega 2 can be written as A sine omega A plus omega B times t. So far so good? Okay, alright. Now I am just expanding all the terms out and then I am collecting all the terms with omega A together and collecting all the terms with omega B together. Okay. So now when you see this signal, what is this particular signal if I plot? What frequency will it have? Just the part within the bracket. What frequency will it have? Yes, Aditya, I'm unable to hear you somehow. Yep, can't hear you.
It will be omega A.
It will be omega A, right? So it will be varying with omega 1 plus omega 2 by 2. Like it has a mean frequency between the two frequency components. It will be modulated by that. Now that whole signal will be modulated by this part, which is depending on purely on omega B, right? So what I'm saying is if I had two waves, one which was having a frequency which is looking like this, and the second was a frequency which is slightly different to it, okay? And I add the two up, I'll see something like this. I'll see an envelope which is varying much more slowly. And I'll actually see the complete signal to be something like this. Is everybody with me so far? Is that making sense? Yes, no?
Yes, sir.
Right? So what is happening here? That this envelope is moving with omega B, whereas the signal's frequency is more or less omega A. So yes, the signal is oscillating with omega A, but the amplitude is again modulated further by omega B. It's like beats, right? Beating phenomenon is what you must have read in your undergraduate, maybe prior to undergraduate, even in school, right? When you learned about simple harmonic motion. So you see this idea that the signal which is coming out now has a slowly varying component, as if the amplitude has a slowly varying component. Is that making sense? Right?
Yes, sir.
So if my ship is now present in terms of these waves, I might expect to see that some sort of this so-called force which is coming at me may depend on this difference frequency. Right? It is a slowly varying force. My drift is happening slowly and I have waves coming at me. I'm not running away with the wave. Each wave is not carrying me with it. Right? I'm not moving with the crest. The waves are going by, but I am drifting much more slowly.
Sir,
Yes.
sir, why isn't it the other way around? Like, Omega B can be in charge of the amplitude.
Hmm?
Omega B can be the amplitude, can be the factor causing the amplitude, and omega A can be the envelope, right?
No, omega B will be the envelope generally. You can try it out yourself. Actually, take a signal, create a signal in MATLAB with two frequencies which are slightly apart. Okay? And then
Yes.
plot them. You should see a
Sir, but
plot
in
which
the
will come out to be exactly like this.
sir, but in the equation we can take out A and multiply it with omega B, and
Yes, yes, you can take out A and multiply with omega B also. Then in which case what is happening? You're saying that in this case, you're saying that my signal is actually varying with this, which is modulated over omega A. You can view it like
yes,
that also. There's nothing wrong with it, with viewing it like that. It is either omega B is modulated by omega A or omega B A is modulated by omega B. The effect is still the same at the end of the day. Right? I'm trying to highlight the difference, just that there are two frequencies here. Doesn't matter which one is modulated by which. Really doesn't matter.
yes, sir.
Okay? You can think of it in either way and you wouldn't be wrong. But this way is more intuitive to see. I mean, it's just apparently clear that the amplitude actually gets modulated by omega B. Can I not think it of as if the amplitude is modulated by omega? Yes, absolutely, you can think of it like that. But it's harder to visualize that intrinsically looking at it.
Yes, sir.
Okay. All right. So the idea here is then that this so-called frequency, which is the lower frequency, you're tending to see certain things which are happening at the difference of the two frequencies at which you're combining things, right? So this is a slowly varying amplitude which you're now seeing. Now add to this the component that your waves are no longer linear, right? So if your wave is no longer linear, you have second order components, third order components, which are having 2 omega 1 times t plus 2 omega 2 times t, things like that are getting added. Yes. Some of this must be familiar from your wave hydrodynamics course. Yes. At least the conceptually you must have heard about these things. Am I right?
Yes, sir.
No, maybe. You're all looking at me very blankly. No, you never heard about this? They didn't talk about higher order wave theories, Stokes wave,
Yes, sir.
and other things.
Sir, we heard about it.
Very briefly, like they went very briefly through this.
Correct. So they went very briefly, but they have talked about these ideas, right? That they have a second order and a higher order components.
Yes.
So when you start looking at those higher order components, these difference frequency effects and the sum frequency effects, they start becoming important. Okay, so you can think of these slowly varying drift forces are things which are coming due to the difference frequencies. Because you are taking the difference between the frequencies, the difference will be very small if the omega 1 and omega 2 are close by. Correct? Which means omega 1 minus omega 2 will be a small value, which means the period corresponding to it will be a really large value. That so-called modulation of the amplitude is happening over a very long period, isn't it? So the drifts caused by those will be very slowly be happening. I'm trying to get you to appreciate. I'm not giving you a precise mathematical answer here. Okay. In fact, actual difference frequency effects, you're only looking at omega 1 minus omega 2. Here we are seeing omega 1 minus omega 2 by 2 because we are only considering linear waves. Okay. The moment you start taking nonlinear waves into account, you'll see that the difference frequency, which is most important, is the difference between the two frequencies of the waves that you are superimposing. Okay, I'm just trying to give you a sense of why that would be important here. We are not delving into a full-blown ocean hydrodynamics course here, but the idea is, can you appreciate the idea that there is something modulated over a smaller frequency range, which can cause forces which are much slower than what the incident waves were. Okay, and that is what causes your drifts to happen, because those are second order phenomena. If I took purely first order phenomenon, my ship should not experience any drift. Okay, is that making sense? Okay, all right. So these second order drift forces, that is why you call them as mean drift forces and slowly varying drift forces. So you saw the slowly varying part basically comes from that so-called difference between omega 1 minus omega 2. Now suppose this omega 1 minus omega 2 is so close that actually they both combine together, then what will that value become? 0. Right? In that case, I have mean components, which means they are not varying with time, but as if somebody is putting a string on my ship and pulling me back slowly. In the limiting case where the two frequencies are matching with each other, what do I expect to see? I should see a mean force acting on it. Is that making sense? Aditya, making sense?
Yes, sir. The amplitude will not vary at that time.
The amplitude will not vary, right? It will have a mean component with which I am getting the force acting on it, which is what is causing the so-called my ship to drift back.
Yes.
Right? Now, if I am moving forward with forward speed, then that drift forces is small, but my forward thrust is more, so my ship is still moving forward. But in essence, what is happening is I am experiencing more resistance than what I had before. So rather than a calm water condition, I'm experiencing a little more resistance. And that resistance is what we call as added resistance. Okay. The theory for this is quite challenging and exciting, not very difficult to understand. The moment you start talking mathematics in terms of second order wave theory and all, you can explain all of these precisely. But that's not what we are doing in this course. So this is just to give a sense of what is going on there.
Sir,
Typically,
just one thing, like this, all of this is being explained using the non-linear waves, right? In linear, if you assume that the waves are linear, this won't happen.
if the waves are linear, then you will not experience zero drift forces. The drift force will be exactly zero.
Okay.
You will not have any slowly varying component, neither will you have any mean component. Nothing will be there. Only when the waves are non-linear in nature will you see these phenomena come in. That is why they are called second order phenomena. If I only consider up to linear wave theory, I should not experience these.
Okay.
Okay? Alright. So which is why I told you, when you look at the ocean, you see these peaky crests and shallow troughs, only then you will see this effect of so-called drift happen. If the waves are of much smaller amplitude, then you won't see them to be this peaky in nature. They'll start looking more like a sinusoidal waves, in which case the drift also will be less.
Yeah.
Okay, so the amplitude of waves really needs to be large enough for the second order drifts to be significant enough. Now, they may be significant on your frisbee that you have thrown in the ocean, but for them to be significant on the ship, they have to be really good large waves. Okay?
Yes.
All right. Okay, so that we talked about the surge force, which is the added resistance. In the sway and the yaw, these wave drift damping is less significant because in general, when you are looking at the sway and the yaw, you'll see a separation occur in the flow. So you're actually seeing vortices being shed, and the damping due to the vortices will be much larger than the forces which you are observing due to this increased drift due to the waves. The contribution due to the wave drift is much smaller compared to the separation and vortex shedding damping coming into the picture. So therefore, we can neglect them in the sway and the yaw component. Not that they don't exist, they may not be as significant. So which is why we typically tend to consider this only for the surge direction in most cases. Because that is where you are thrusting, you are providing a thrust to move your ship in one direction. So it makes sense to account for that additional resistance that you are getting. Okay, all right. I think we have spent a good amount of time here. So now that I talked about vortex shedding, it makes sense to now discuss the next dissipation phenomenon which is coming due to vortex shedding, right? So a typical vortex shedding drag, you can express it as half times rho times a drag coefficient times the projected area of the cross section and times the velocity of the craft, right? So this is a typical formula for a drag coefficient or the drag of a vessel, where this drag coefficient is now dependent on so-called Reynolds number, where Reynolds number is given by U times some characteristic length of the body divided by the kinematic viscosity of the body. You can kind of identify that this is what you have seen in the so-called second term of the Morrison's equation. Yes, you've seen this before somewhere. Okay. So it is similar to what you see in the Morrison's equation. For a typical salt water, we'll take with salinity about 3.5% at 5 degrees centigrade. We can see that nu is about 1.5 into 10 power minus 6. Typically at more closer to the 25-26 degrees or the room temperature, you will see this kinematic viscosity will be close to 1 into 10 power minus 6. In most examples, you can kind of approximate it as 1 into 10 power minus 6. Okay, in addition to that, we'll also have some damping caused due to the forces or the so-called lifting forces, which means that when my vessel is drifting, you saw this, some of you saw this when we were doing the test yesterday, right? When the vessel is turning, it is actually having a drift angle, right? If I consider from far, I can look at the ship as an aerofoil section in a uniform flow. It will have forces which are acting on it, right? Lift and the drag forces which are acting on it. Now the point is that those lifting forces which are acting, they will be responsible also for some sort of damping on the vessel. Okay, depending on how I take the components along the surge and the sway direction, they may also contribute to certain damping in certain modes. So I'm just trying to tell you here that that so-called dissipative damping term which we are looking at in this equation of motion may have multiple sources. And we are just discussing what are the different possible sources from where this damping might come. It can come from potential damping, it can come from skin friction, it can come from vortex shedding, it can come from lifting surfaces, it can come from quadratic damping due to boundary layer effects. So this is what we are just having a rough discussion on what are the causes for these dampings. Typically, you can't model them very well, especially for the full scale. So what we do is we do the next best thing. We either try to do some smaller experiments at certain Reynolds number and try to do an extrapolation. But what really happens in a real scale ship cannot always be modeled perfectly due to scale effects. Because most of our scaled models are operating at Froude scale, right? We are matching the Froude number between our model and the prototype, which means the Reynolds number definitely does not match. Right? So therefore the drag that I experience on my model cannot really be scaled back up to the full scale, precisely at least. Right? We try some approximations or we try some sort of wind tunnel experiments sometimes to try to get past this problem, but that continues to be a problem when we are talking about ships. Because whenever we are scaling our models using Froude law, there will not be a Reynolds number matching between them. And so therefore those scale effects will always be present. And they are important to understand that our experiment may not represent reality 100%. In certain dynamics, yes, it will, wherever waves are involved, because surface gravity waves follow Froude number, we can scale those effects dynamically. But anything which is having to do with viscous effects, we really can't do the scaling properly. That is what is referred to as scale effects. Which is why when we perform the turning circle maneuver using a scaled model and we apply it at different scales. So let's say I build one model with 75.5 scale, one model with 35 scale. So my model will be larger. The turning circle will not be the same. the non-dimensional turning circle which you get from both these hulls will not match, precisely because these so-called damping dissipative forces that you are measuring on the hull, they will scale with Reynolds number, so there will not be a corroboration there. I hope I'm making sense here. Yes? Right? So these are called scale effects which one has to be taking with a pinch of salt whenever we are doing these experiments. Okay, so we are just having a discussion about it, that when we are talking about so-called dissipative approaches, these things need to be taken into account. Again, these so-called lifting forces can be of linear or non-linear in nature, depending on what is causing them. So in general, we can write that total damping matrix can be approximated as some linear damping matrix D plus a non-linear damping matrix Dn, or N stands for the non-linear component. Okay, and it can include terms which are quadratic in nature or even higher order in nature. And the linear damping usually gets contributed to by the potential damping or the skin friction due to the laminar portion of the boundary layer. Okay, so the linear damping in general can be shown to be a matrix which is composed of cross couplings between the sway, roll and yaw. You will see some cross coupling happening between them. So this is sway to sway, sway to roll, sway to yaw. This is roll to, what do you call this, sway, roll to sway, roll to roll and roll to yaw. Similarly, yaw to sway, yaw to roll and yaw to yaw. Similarly, you'll also see a cross coupling between the vertical modes, the so-called the off-center plane, so which are happening in the vertical plane, so which is surge, heave and pitch. So you see heave and pitch are coupled together. Typically, you will assume that the surge is decoupled from others, but in reality it is not fully decoupled, but the effect is less. So it is okay to try to ignore that for many of our modeling purposes for simplification. But in reality, you will actually see the surge is actually strongly coupled with pitch. Okay? As I move my model forward, I also expect it to go up or down a little bit. That is natural to expect it. But for most practical purposes, we can disregard it, because in the surge we have a propulsion unit which is operating, so which can overcome these effects fairly well. So we are not really worried too much about it. So for most modeling purposes, we can choose the surge to be an independent direction, which is why you will see all these are zeros. Okay, so this is what a typical damping matrix for the linear damping will look like. Okay, and for a surface vessel, we can simplify this as before, and I think you have already seen this before when we talked about where you have the, we saw a similar effect with the added mass matrix, but now we are discussing the so-called damping matrix. Again, the cross coupling is there between the sway and the yaw. And these are nothing but zero frequency damping values, which you can pick out from typical potential flow programs. And then you have to also model some skin friction part, because the viscosity is important when we are looking at very slow motions. Okay, we will stop right here. And in the next class, we'll pick up nonlinear viscous damping in surge. So we have looked at what is happening with this so-called linear damping matrix. In the next class, we'll try to look at what is happening with this nonlinear damping. What are the different models to model it? Once we finish with the damping, we will start off talking about what are the different models, complete modeling of sea keeping and maneuvering, or which is a 6 degree of freedom equation of motion, which incorporates all these dissipative forces and everything in together. So that forms our core model of the craft. That is the dynamics which we then need to control. So that will be the later half of the semester. So we'll try to wrap that up maybe in 1 to 2 weeks. Any questions before I close off? Or I stop the recording? No questions? Or you want to think about it for a minute? Okay, let me stop recording.